All right, calculus friends, I feel like I've left you stranded long enough, and so I need to give you a little bit of information here that might help you out. This is the activity that you were supposed to be working on Monday, and it looks like everybody did it. I kind of went through and I saw what you did, and it seems like you kind of got the idea. We have here a graph that has the rate on one axis and the time. So this is showing a traveler going through the great state of Nebraska, where clearly you would not change your speed the entire time. There's nothing there to slow you down. There's nothing there to speed you up. So if this person is traveling for 4 hours and they are going at what appears to be 75 miles per hour, you could just take 75 times 4, and that would tell you that the total distance is 300. And so what we're trying to do here is connect that if we take an area that is bounded by a line and the x-axis, and then we put boundaries on either side, we're defining an area. We're talking about the graph of a rate function over time. The area underneath that curve is going to represent the distance that we travel. Okay, so this is the opposite thinking of when we were talking about derivatives, and we would have a graph that would show our position, and we would find the slope to find the velocity, which was the rate of change. Okay, so this graph is boring. This graph is like not very exciting in any way, shape, or form. The next graph here that you came to is a slightly more intriguing journey, where now you have areas that are going to be not quite as easily to find. So you see here between 0 and 2, we have a rectangle. And then we have a little triangle up here that you would want to count for your area. We have a rectangle here, and then maybe you make it into a trapezoid. You could find the exact areas here because these are straight lines. The shapes that are underneath here are all shapes that you should know how to find the area of from geometry classes. And so, again, no big deal. We could actually find the actual distance this person traveled. In fact, some of you might have done this in physics. In physics, especially at a high school level, try and keep the graphs to nice, neat shapes that are easy to find. Okay, then we kind of work our way up to this monstrosity here, where we have a graph that is curvy. We have a terrible driver here, and we are now looking to find the area underneath this curve. And no matter how we try and piece together little sections of graph here, we're not going to get the exact area because we don't know how to find the area of blobs and things like that. I hope you enjoyed the blob box challenge. Also, I'm not sure if those ever got to you or if you even attempted that. But if you did, maybe you thought about different ways to figure out the area of irregular shapes like the one that we have here. Okay. This is the situation that we are most concerned with right now. We are trying to find the area underneath just functions, okay? And so if you've been doing the work in class, you know that we're dealing a lot with rectangles. So we're going to take this region here, okay? And whenever we're talking about a region, it's important to understand that the x-axis here is one of our boundaries. And so it's not like this area goes on forever as we go down towards the bottom. The area is defined here from 1 to 5. We have the x-axis as a boundary, and then we have the curve as a boundary. And we'd like to figure out what the area is in here. Not just an approximation, we'd like to know what the exact area is, okay? So what I had you doing here is dividing this up into smaller, equal-sized sub-intervals. So let's say that we had 4 sub-intervals. Okay, when we have 4 sub-intervals, okay, it's 4 spaces to go from 1 to 5. 4 subintervals, each one of those intervals would be 1 unit, okay? So to figure out how wide each one of our rectangles is going to be, we take the right endpoint minus the left endpoint, and we divide it by the number of rectangles that we're going to make, okay? If we have 8 here, now all of a sudden each one of these is 1/2 of a unit. If we made it 12, each one of them is going to be 1/3 of a unit. Okay, just to make this kind of easy, let's just go with 4. And so each one is a nice, neat 1 unit here. Okay, so submit to teacher. I am the teacher. Here we go. All right, so now that tells us how wide each of the rectangles are. These are approximating rectangles. Okay, now this becomes like the huge issue with trying to figure out what's going on in sections 5.1 to 5.3. if I want to figure out how tall each one of my approximating rectangles are going to be, I want to come up with a consistent strategy. So I can use the left endpoints of each interval, which usually the book will write a big L if they want to do that. Right endpoints, which is the farthest point to the right on the interval. We could use the midpoint. We could actually use anything in between the two spaces here, okay? So my first interval here starts at 1 and it goes to 2. Overall, it's 1 unit. The left endpoint is x equals 1. The right endpoint is at x equals 2. So if I'm going to approximate using rectangles and using left endpoints, I'm going to figure out what this function is equal to at 1, and that's going to be the height of my first rectangle. Then I'm going to figure out what my function is equal to at 2, because 2 is the left endpoint of the second interval. At 2, my function is equal to 4, because it's x squared, so 2 squared is 4. At 3, the function is equal to 9. At 4, the function is equal to 16, and we can see these points forming on our graph. So we have 4 intervals here. For each one of the 4 intervals, we figured out what the function is going to be at the left endpoint, and then we're going to use that as the height of the rectangle. All right, so going on to the next screen now, you can actually see the rectangles, okay? So this first rectangle is 1 unit for the width and 1 unit for the height. So that's going to be a total of 1. The second one is going to be 1 unit here and then 4 for the height, okay, which equals 5. Third one is 1 by 9. Now I'm up to a total area of 14 plus 16. That's not 16. That's 16. All right, so now my area here, my area approximation is 30. But that is a crappy approximation because there is a ton of extra white space here, okay? This is what we call an under approximation. It is less than what the area actually equals. We do know, though, that our area is at least 30, okay? The idea here with the rectangles is the more rectangles we create under here, the better the approximation is going to be. So if we made 100 rectangles, it would take forever to actually find the area of each of those. We have to do 100 different areas. We would have a better approximation, okay? Because this is calculus and we're dealing with limits, if we think about the limit as the number of rectangles goes to infinity, that's going to be what the actual area is equal to. Okay, so now we're looking at this graph right here. Okay, so now we've got the area calculated as 30 when we have 4 rectangles. This slider makes more and more rectangles. Okay, so now we have here 36 rectangles. Okay, there's 36 rectangles here. Each one of those rectangles has a width of 4 over 36, which is 1/9. Desmos here is adding these all up. It's telling us our area is 40.00 right now. You see that there is less error here. There is less empty space. This is a better approximation. The bigger that I make this value of s, the better the approximation. And you start to see at a certain point here, that area really doesn't change a whole lot as we go, okay? That 41.28, somewhere around there, seems like a really good approximation for this space here, okay? The more rectangles I make, the better approximation I could say, okay? So the actual area here, the actual area underneath this curve, this actual shaded region is going to be the limit as this number here, the number of rectangles, gets closer and closer to infinity, okay? When you see like delta x in homework assignments, delta x is the width of the rectangle. When you see n, n usually represents the number of rectangles you have, okay? We could also use the right endpoints. Now, if you go back and you think about that here, if we have this right here, my right endpoint would be 2 here. So if I use my right endpoint, I would actually be over approximating what's going on here. My area, my first rectangle then would be 4. My area, my second rectangle would be 9. Then I would have 16. Then I would have 25. Okay, if I'm using the midpoint, I would figure out what the function is equal to halfway in between at like 1.5, and I would use that to figure out what the height of each rectangle is. Okay. This last one on here was on here to just get you thinking about what happens if we have area that is below the x-axis. Okay. The weird part about what we're going to do is we're going to actually consider the stuff that's below the x-axis to be a negative area. So in this case right here, the area total would be 0 because the positive area matches up with the negative area. So I know right now that some of you might have this completely figured out. Some of you might still be trying to get yourself back into the thinking from break. I'm not planning on giving you a quiz or anything on what we're doing this week. Any of the final exam questions that deal with stuff from chapter 5, we can figure out like what to do with those next week. Maybe not grade them, maybe just kind of use them as like how are we doing on this right now. My goal right now is to be back on Monday. If you have any questions about things that you don't understand, just send them to me and I can try and answer them and maybe make like another little video tomorrow about like, hey, here are some questions that you had and this is how you solve them. If anybody out there has anything that they're worried about with your grade, with like Project ICE, with a test you got to make up or something like that, if you're really worried about it and you need me to answer, just send me an email and I'll send it back to you and we'll get that all straightened out. Don't stress out about something. If I like need you to make up something, I'll try and let you know that I need you to make it up. Also, if you see something in the grade book that doesn't look like it's right or isn't, just let me know and we'll get it taken care of. I'm hoping to get a couple other Project ICE videos up today. I hope all of you have a great day, and I'm really looking forward to seeing everybody soon. Hopefully be back really soon, hopefully by Monday. Again, please send me any questions if you are having them.